it has length L, net charge Q. We'd like to find an expression for the electric potential, which is some distance Z above the center of the rod. So let's just start with another sketch of this rod so we don't have to mess up this drawing. Here's our rod that's got total charge Q. Let's get our coordinate system on there. Put the horizontal right down through the center of the rod. Put the vertical right up through this center of the rod. We're going to try and find the electric potential at our point P right here. To find our electric potential, we'll start by identifying some small amount of charge, dq. dq makes a small amount of potential, dV, at point P. Notice we don't draw that potential because it's not a vector. We can't draw it. It's a scalar quantity. And that little bit of potential is K, Coulomb's constant, times the amount of charge dq, divided by the distance between the charge and the point. Let's draw this in the diagram. The distance between the charge and the point is from here to here. How are we going to find our r? Well, we notice that r is the hypotenuse of a right-angled triangle, where this distance is x and this distance is z. So r is the square root of x squared plus z squared. So we can fill this in for our r. What are we going to do about our dq here? Well, the size of this charge dq, the amount of charge on this element of charge, is the charge density times the length of this charge. The length of this charge is a little bit in the x direction, so the length is dx. So lambda is the charge density. And that's the net charge divided by the length of the rod. So let's fill this in for our dq. So there's an expression for the small amount or the element of potential created by that small amount of charge. To find the total potential, we have to add up the amount of potential made by every little bit of charge along that rod. So let's fill in what we found for our element of potential dV. First step to simplify, let's take k and lambda out front of the integral. So now for our next step, let's identify the limits of our integral. We go from one end of the rod to the other. So one end of the rod has x equals minus L over 2, because this line goes straight up through the center. So our x initial goes from x equals minus L over 2. Our x final is over on this end of the rod. That's x equals plus L over 2. So let's evaluate our integral and put in our limits. So you can either evaluate this using your integration techniques, or you can look up the answer in the book. So this integral gives us the natural log of x plus the square root of x squared plus z squared. And z is our distance between the center of the rod and the point. That's going to be evaluated at x equals plus L over 2 and x equals minus L over 2. So we'll fill in those limits. So x squared here is L over 2 squared, gives us L squared over 4. Minus L over 2 squared is also L squared over 4. If you left your answer like this, it wouldn't be the end of the world. We can simplify it a little bit. So let's use the identity that the natural log of A subtract the natural log of B equals the natural log of A divided by B. Let's use that identity to simplify a little bit. And then we could leave it like this, or we could just simplify one little bit further. For our argument inside the natural log, let's multiply by 2 over L on top and 2 over L on bottom. That's just going to give us a slightly simpler look. As I said, if you left your expression like this, it's absolutely fine. That's correct. It's just not as simple as it could be. So let's just finish it up by multiplying by 2 over L on top and bottom. L over 2 times 2 over L, that's 1. Plus, we'll multiply our 2 over L inside the square root here. So when we multiply that inside the square root, so we'll square the thing and put it inside. So that gives us 1 plus 4z squared over L squared. And we divide that in the bottom. Minus L over 2 times 2 over L gives us minus 1 plus L squared over 4 times the square root of 4 squared over L squared gives us 1 plus 4 times z squared over L squared. You could probably tinker with this a little bit longer, but I think it's pretty good the way it is now. And here's an expression for the potential, a distance z above the midpoint of the rod. The last thing we'll do is, we know that the potential has to be positive, so let's put in some absolute value signs. And we know the potential has to be positive because the charge is positive. So there's our expression for potential that we were asked to find.